Welcome, everyone. First, I'd like to thank everybody for coming out today, both in person and online, and joining us here for the first panel as we kick off the Nano4EARTH Challenge. For the panel today, we have several different goals that we'd like to accomplish. The first and most primary, to identify and discuss some emerging or interesting areas where we think nanotechnology is going to make an impact in climate change and progress towards those goals. If time allows, we'll also try to touch in on how the NNI and federal agencies can help catalyze some of the goals in the nanotechnologies as we push towards these applications. And then finally dig in a bit on Nano4EARTH as what topics are really relevant and that we really want to focus on. And so we're very fortunate in this case that we got three outstanding panelists with us today. Some coming in last minute, a lot of flight troubles. But exceptional backgrounds ranging from leading research teams, working in startup companies, and also starting to drive both the national policy and international aspects for climate change. So with that, we start off with just a quick warm welcome for our panelists. And I'd like to let them each have a few minutes to introduce themselves. And Sally, we'll start with you.
Okay, anyway, hi everybody. I'm Sally Benson. I lead the energy team at the Office of Science and Technology Policy in the White House. And my job is to work with the agencies to develop a national innovation agenda to make sure that we can meet our climate goals of net zero emissions by 2050. So if we look across the landscape for climate solutions, there's obviously a huge amount that we can do now, but about 50% of all the technologies that we're going to need to get to net zero are either in the demonstration stage or perhaps even earlier. And so we have a lot of work to do over the next decade or so to make sure those technologies are available when and where we need them. So I lead something called the Net Zero Game Changers Working Group. And I have the privilege to work with fantastic people at all of the federal agencies who work in the climate innovation space. And we have identified 37 different game-changing technologies, and there's a report about that, U.S. Innovation to Meet U.S. Climate Goals. So if you want to take a look at that. And that was released last month. And basically what we did is we have this list of 37, that's a long list. So the question becomes, which of those deserve the attention first in terms of the impacts they can have. So what we did is we looked across a number of different criteria, in particular the greenhouse gas reduction potential, and we bin them, less than 100 million tons a year to 100 to 500 million tons a year, and then greater than 500 million tons a year. In other words, a really huge impact. But we didn't want to stop there because we all understand that energy is so deeply woven into our society that we have to make, at the same time, we have to make sure we're meeting other goals. So particularly, we looked at which of these technologies has the biggest potential to protect and restore ecosystems, which of these technologies has the biggest potential to address environmental justice concerns, where are areas that they could really help with economic development by creating good new jobs, and also the degree to which they could contribute to national security. So based on this, we categorized them, looked at their impact, and bin them according to whether they had transformational impact, meaning they had huge benefits across all those categories. They had broad impact, meaning, yes, they're super important, but perhaps don't address so many needs. And then finally, what are those with targeted impact, meaning we've got to get them done, but they perhaps address only a narrow sector of our emissions. Again, I encourage you to take a look at this. We picked 5 of the areas based on their potential impact for early focus for the Net Zero Game Changers Initiative. And I'll give you what they are, just in case you're interested. So the first one is a zero emission grid and electrification. This collection of 2 critical actions can get us about 50% of the way to reducing our emissions, so incredibly important. Second one is zero emissions heating and cooling. basically HVAC systems, and that's a large fraction of our emissions today from buildings, but also looking to the future, that's going to grow around the world as climate becomes more extreme, and also as developing economies are able to access the comfort that's provided by HVAC systems. Next one is net zero aviation, a small but growing segment of our emissions. And then the next one is really a big one, industry. So much of the industrial processing that we do today was built upon the fact that we could use combustion as a primary source of heat and as a way of accomplishing the chemical reactions that produce the products we need. In a world where we're considering or we're concerned about CO2 emissions, but in addition to that, other emissions of pollutants to the atmosphere, can we imagine a post-combustion world where we use a different set of core processes to produce all the goods our society needs? And could we move to a system where we're much more circular, meaning that we don't make things and basically throw them away, but keep them in the economy so that we can, over time, reduce our reliance on extractive industries that also come with a lot of environmental issues. So that was the fourth one. And the last one is fusion energy. Again, an entirely new technology, a new source of energy here on Earth that basically replicates the processes in the sun, but in a controlled way. And of course, I know you all heard about the very exciting development at the Livermore Laboratory at the National Ignition Facility, reaching a benchmark accomplishment due to the great science and engineering of US scientists. So that's our list. I'm just going to say one more thing. So when I first thought about this list in nanotechnology, I went, you know, if I were looking at the intersection between this list and nanotechnology, maybe I wouldn't have, said this is the biggest set of opportunities. Having said that, though, I just decided to do some Googling. My favorite one is looking at HVAC systems, heating, ventilation, cooling. What pops up right away? All these people are developing new refrigerants that use nanotechnology, right? So I thought that was really super cool. So actually, when I went across this list, nanoscience and technology could play a major role in addressing all of these areas. And with that, I will stop. Thank you.
Thank you, Sally.
Sure. Good morning, everyone. My name is Michelle Ostrat. I am the Chief Scientist for Pajarito Powder. It's a startup company based in Albuquerque, New Mexico, and we're looking at developing advanced electrocatalysts for applications in electrolyzers and also in fuel cells. Previous to Pajarito, I've had a long career in nanomaterials. I've been involved in nanotechnology for over 20 years, largely in very large companies such as DuPont and Aramco. I've also spent some time in the not-for-profit research area when I worked at RTI. So my background is really in being able to utilize advanced materials to be able to help advance discoveries and innovations in a broad set of different industries, including defense, energy, health, and the environment. And one other thing I would mention, because it was also part of the keynote speaker's question towards the end, I've also been very involved in nanotechnology, occupational safety, and health. Being able to understand when you have an emerging area such as nanomaterials and nanotechnology, one of the first things you want to do is make sure you don't do any harm. And so that was an initiative that we ran many, many years ago. First of all, to be able to protect workers who would be potentially the first people who would be exposed to nanotechnology and nanomaterials. So that's some work that I'm also quite proud of as well. So looking forward to this panel.
Yeah, thank you.
Sure.
Yes, Senior Director, Geotech Center at the Atlantic Council, which is probably not too familiar to this group, but this group is quite familiar to me. I've been involved in nanotechnology and nanotechnology shift for a long time. I can't quite seem to escape it. In fact, I would say I got started with the person who's here in the room here, Jim Murday, who's sitting over there, who had the misguided idea I might be able to contribute to nanotechnology very early in its field of the Naval Research Laboratory. So I did some useful work as a scientist there for quite a while, and then moved into management. I spent time as the founding deputy of the Center for Nanoscale Science and Technology at NIST, which led me to some interactions with the White House and the National Nanotechnology Science and Engineering, Nanoscience Engineering and Technology Subcommittee at the White House, which actually led me about 9 years ago last week to step in as the interim director of the NSEO, which is Brandon's current role. Closer. So that was sort of my shift to policy, and then I spent quite a bit of time at the Office of Science and Technology Policy, working on the National Nanotechnology Initiative, a little bit of time then at the National Science Foundation, and then left the nonprofit government for a different nonprofit, the Atlantic Council, which is a really historic institution known for promoting good global relationships, and as we like to say, shaping the global future together through international relations. It's not historically a strong place for science and technology policy on its own, but that's one of my jobs in joining the Atlantic Council. So at the Geotech Center, we look at emerging technology broadly and are trying to understand, what it will take for a range of emerging technologies to essentially enter into the world across the globe for the public benefit, and also looking at what the sort of downside geopolitical risks are in that area, and that ranges pretty much across the board. So nanotechnology continues to be an interest of mine, and in particular, having been involved in nano for a long time, it really does inform a lot of both the good and the bad of approaches. What has the NNI done right, and what are, in particular in the early days, errors perhaps in engaging the community that led to some sort of adverse effects of nanotechnology in terms of policy around the world. So I think there's a lot to learn from nano, and including now in the climate space, as to how to best approach it. I would say, in my view, the most important thing is really to think about these things, and I think I applaud the NSEO for doing this, at a systems level, right? And when you're talking about nanotechnology, to think about all the different ways it can solve problems and try not to focus just exclusively on the individual technologies at hand. The other big part of that is the importance of not just focusing on the science, but also, especially in areas like climate, where some of the applications involve the environment or other parts of the ecosystem, to make sure that the scientists are engaged also in thinking about, or at least engaged with people thinking about policy and public engagement. Because without that, I would say you run into the danger of none of the technologies that you want to use actually ever seeing the success in their applications that you think they could.
Thank you, Lloyd. All right, so you see we got a great group here to work with. And so, like I say, we want to focus our time on digging into the actual nanotechnologies themselves. And as we're having this discussion, we definitely want the audience involved. So if you have questions, feel free to come up to the microphone. And the same for online, shoot the questions in, and we'll get those up to the panel as we go. We will have an allotted time at the end as well for Q&A, but if the topic is something you want to jump in on, don't wait for the end, jump on in. So to start with, as we say, some of our goals here is to really identify and discuss some key nanotechnologies that are of interest to you guys that you see as emerging and has a high potential for impact. I don't know if it's me. So to start with, though, I'd like to do a little rapid fire down the line of just some of the top ones that come to mind, maybe 2 to 4 that you think have the impact, and then we'll circle back around and kind of start to dig into them. So maybe we'll start down there with you, Lloyd, let you start up, and we'll bring it down this way.
Sure. I should make another comment that what I talk about is my own opinion, so I talk from the Atlantic Council, I don't talk for the Atlantic Council. So I'm going to raise two. I have a particular interest in discussing what's somewhat controversial topic that a lot of people literally think we shouldn't talk about, which is solar geoengineering and some of the larger aspects of that are scalable and could either remove carbon dioxide from the environment, CDR, or change reflectivity and other things of the planet. I think there's actually some really intriguing nanoscale nanomaterials applications there. There's a lot of debate about whether one should even talk about these, but I would make the case that it's important to have conversations early about controversial technologies, But those are two that I find really intriguing that many people actually don't want to talk about. I'm happy to talk about them to help instigate that conversation.
Right. And so given my background in industry and very large industry, a couple of the technologies that I think have a real potential for being able to utilize our energy that we were already producing more efficiently, particularly in large industrial processes. I would put catalysts at the very top of that list. I'd put membranes at the top of the list. So much energy is used in driving chemical reactions, and catalysts can make that energy be more efficiently used, which means you need to produce less of it. And I'm just amazed at the number of industrial processes that require some kind of separation or purification. And membranes and sorbents, other those types of materials have a huge potential to enable large industrial problems to be able to use their energy much more efficiently. And the last one I would put in is got to be batteries, just to be able to provide more of a link with the inconsistent renewable energy generation, with the fact that we need to be able to utilize energy not just when the sun goes up or when the wind is blowing. So I think batteries are really going to be critical to be able to tie together the renewable generation that we have with the energy demand cycles that we need.
Okay, gosh, I think you're going to find that we are kind of in violent agreement. So maybe I can just put a little bit more color on this. So number one, I just want to say one thing. Looking across the list of 37 technologies, I think nanoscience and technology has an important role to play in all of them. So I don't think that the list of three should, exclude focus on the other ones as well. So having said that, okay, first one, batteries. So batteries have made remarkable progress, tenfold drop in prices. It's now, affordable to make electric vehicles and so forth. But that's light duty cars, right? So as we look to the future, there's more things we'd like to electrify. We'd like to think about electrifying heavy duty transport, right? That's still really hard with batteries today. We need higher energy densities to be able to do that. What about shipping? What about rail? What about planes? What about hybrid planes, for example? So we need to expand the capabilities and the performance of the batteries to be able to address multiple sources of transportation. Second one is on grid scale storage. It turns out when you look at like a cost optimal grid or the cheapest grid you can buy, even short-term storage actually has a hugely important role to play in terms of meeting, peak demand and so forth. So I think that even today's platform technologies can have a big benefit. But we would like longer duration batteries. We heard about the long duration Earthshot. That's important, critically, focuses on sort of the 10-hour battery, basically how to get you through the day. That's certainly very important. And not only does it do day-night, but what we're finding is that resilience is increasingly important. So having backup systems that allow you to ride through extreme weather is going to be important. So that's batteries, so very important for lots of areas. Second one is long duration storage. And when we think again how important energy is and so forth to the economy and health and so forth, having an entire energy system that runs sort of on demand, does not give you the sense of security you need, knowing that there was really a big pool of energy stored somewhere that would be available to you. And if you look at the options for really long duration storage, and what I mean is weekly to seasonal storage, which most grid models suggest you're going to need, unless we're going to rely on other forms of clean, firm power like nuclear, is we are going to need to think about this seasonal scale storage. So the question becomes, what kind of technologies would be able to provide that? Well, liquid, high energy density liquids, including those with, carbon-hydrogen bonds, are an excellent candidate for this. So basically chemical storage And so things like e-fuels or electrofuels are very, very good option. And if we think about the nanotechnologies required for that, clearly catalysts are very important, but also separations. So very, very important area. And then the final one, again, with our violent agreement, is carbon capture. Every major model that looks at, well, not every, I mean, there are some that don't require this, but many of the models suggest we're going to need a significant amount of carbon capture from industrial sources. In addition, we're going to need to extract carbon dioxide from the atmosphere. And today, these processes are very energy inefficient. There's huge room for improvement. So if you compare, for example, the minimum work for CO2 capture to the actual performance, there's like a 6 to 10x, room for improvement. So that's a really great target to go after. There's a lot of exciting work on new materials for doing this, as well as new processes. But I want to sort of add one more thing to the table. If we're going to all the effort to remove carbon dioxide from the atmosphere, why not think about in that same process, just doing also methane removal, also nitrous oxide removal. So remove all the greenhouse gases. Just do it in one fell swoop. So we need to think about what are those kind of materials and processes could we add to direct air capture of carbon that would help us go after these other greenhouse gases. So anyway, my list of 3. Thank you.
Perfect, and I like to see the overlap there. It really gets some concurrence in it, and I see a few main areas that I think we'll start to delve into a little bit. Actually, let's start with the carbon capture and storage a bit. So as we think about that field, and actually we'll just open this up to the panel as we go, what are some of the fundamental challenges with the material development, specifically with the nanomaterials that might be enablers in this field? So I guess open it up. I don't know if I can go.
Yeah, my mind in this one doesn't actually go to the materials. It goes to some of the other challenges associated with the geological structures, the leakage, the long-term type storage. So my mind doesn't immediately go towards the
we can elaborate on that
towards
too.
the materials.
Because a lot of this can be like, look at what the challenges are, and we've got a lot of smart people in the room that might start to think, well, how can I help solve those problems? So it doesn't have to be just materials. You're right.
Yeah, maybe I'll add. I mean, basically, I mentioned that today the amount of energy that it takes to capture carbon dioxide is very high compared to the minimum work. And the fundamental reason is the main technology that's used today, solvent technologies. These are aqueous solvents that basically need to be absorb carbon dioxide at a low temperature, and then they need to be heated up to release the carbon dioxide. So basically it's a temperature swing process. And most of the substance, the solvent, is water. So the main technology that you are using, or we're using today, basically you have to boil water for every cycle that you're running through an absorber, and a regenerator tower is heating and cooling water. Well, that's a massive sink for energy. So if we had materials that were really good at grabbing onto the carbon dioxide, but then didn't require too much more energy, or perhaps didn't require thermal energy, but could use electrical energy or pressure swing, that we could dramatically reduce the amount of energy that's required. So there are people who are working on sorbents, basically solid phase materials that can do this process. Metal organic frameworks, we heard from Dr. Berhe some exciting examples, but these technologies are not yet mature enough so that they're beginning to make their way into the marketplace that would support, for example, large-scale demonstration projects. So that's really a big opportunity. And then I mentioned, wouldn't it also be great if not only do they remove this carbon dioxide, but they could remove some of these other materials. So would it be a similar material, or would it be an add-on to the process that could strip the methane and other greenhouse gases? So
with that in mind, is there a thought that, it might be a multi-material system to address each target gas, or there might be?
Well, that's a really great question. I don't know the answer to that. Yeah.
So, comment. So one, which are related. So one is, given the scope of the problem, these kind of things, one of the big challenges is making these technologies that are really scalable, right? Because if you're going to have an impact on carbon dioxide or other greenhouse gas reductions that are actually going to have a measurable effect, they have to be really, really widely deployed. So that's somewhat of an engineering challenge, but it also comes back to the sort of policy issue to the extent that we're talking about engineering nanomaterials, then we have all of the nano-EHS questions that have sort of in some ways plagued the nanotechnology community for a couple of decades, right? So once again, it's going to be really important to think about and engage the communities and people who might worry about whatever those materials are being used at scale and whatever that application is be, whether it's underground or in industrial processes, so that we don't end up with some of the challenges we've had in the, for example, materials in the medical community with EU regulation versus US regulation, other things that would ultimately, prevent these solutions from actually being applied.
So I'm actually going to build on that a little bit because I completely agree with something that you said around, being able to understand the scale of these problems. And I'll tell you, for about 6 years, I ran a research center for Saudi Aramco in Boston. And that's a big oil and gas company, right? It's really impactful when you go to those facilities and you see just the scale of what it takes in the petrochemical industry. And one of the things I always was really struck by was how, and this is maybe going to be a little bit controversial, but I'll say it anyway, how mature and energy efficient petrochemical really is. It's a really hard thing to kind of outperform, something that's so established and it's so energy efficient. But really being able to look at those technologies that can start to compete at the scale that the petrochemical, and I'm including oil and gas production, but I'm also including things like plastics, the manufacturing. Those were some really tough benchmarks to try to outperform. And so I'm just gonna...
Well, I mean, this is why people would say that decarbonization is so important, because you're not going to do any good sequestering it if you're putting out more than right. So that's part of the scalability challenge, right? But it's also part of the larger economic and policy challenges of decarbonization.
Right.
And then also looking at the economics of it, as far as ongoing investments in new materials and new technologies in this front, is it already kind of well established, or is it an area where there's kind of a need for maybe the NNI or other to really put a focus on new materials development?
Yeah, maybe I can say a little bit about that. I mean, certainly there is a very vibrant startup community and academic research community that is very interested in nanomaterials for carbon capture. And the Department of Energy has supported energy frontier research centers related to this at a number of universities and labs across the country for more than a decade. So there's certainly a lot. In terms of though, are we, going to that next scale of investment? I think we're starting to see that, but we're also in a situation where there's an imperative to get some of these projects going, and when you consider the level of investment required, people are trying to minimize project risk. So what we see for the very large scale demonstrations are people who are largely going with established technologies. Having said that, though, again, the Department of Energy and through the infrastructure law is going to be establishing a number of major R&D and demonstration hubs associated with direct air capture, so that, as well as carbon capture. So I think that a lot of the innovations that have been nurtured and incubated in the laboratories, both private sector and public sector laboratories, over this next 5 years, we're going to see a real explosion in the further development of those technologies, which I think will be really exciting. I think what we need to do is make sure that there's that feedback loop that draws on the experience that we're getting from these demonstration projects and feeds that back into the innovation cycle so we can continue to make those improvements. So I think that when we ask what can Nano4EARTH do, I think creating that ecosystem where the learning that is taking place as we start to scale up these technologies feeds back into the cycle that will allow improvement is going to be really crucial if we're going to go quickly.
And I'm glad you said that. I'm glad you brought up like the 5-year time frame, because it's one of the things that we want to think about in the realm of this challenge is what are our opportunities for the near term as it goes. So it sounds like this might be an exciting field in the next 5 years that we might see a lot of progress, making the connections, to help push this forward. And actually, I think we have a question from online.
A question just came in online directly to Dr. Benson's comments. So if we're using resources to capture CO2, should we be investigating more ways to use CO2 as a feedstock for chemicals to replace fossil fuels? Also on the topic of materials development, do we need better catalysts to crack CO2? And that comes from Sam Brower at NanoViz.
And that might actually then start tying into catalysts, which might be one of our next ones. So actually, it sounds like it's a little bit on carbon utilization. Once we capture it, are there opportunities to then apply it?
Yeah, absolutely. That when I mentioned e-fuels, electrofuels, the key idea is you take carbon dioxide that's captured from the atmosphere or from some kind of industrial processes, and you basically synthesize fuels by combining that carbon dioxide with hydrogen, clean hydrogen. So yes, utilization is important, and I think that also brings up sort of the broader issue of the petrochemical industry that you mentioned. Today with a barrel of oil, it provides so many products, right? We're most familiar with gasoline or diesel. But that same barrel of oil is used to make a lot of chemicals. And the economics of the petrochemical industry is closely associated with the idea that you try to get as much as possible out of a single barrel. Well, if we are not using as many fuels, we probably still need all these other materials. And how are we going to make them? And certainly there are bio-based pathways for making some of these other products or making the feedstocks that allow us to do them. But there are also electrochemical processes which involve CO2 utilization, which can create the sort of next generation of product substitutes as we move away having so many of those barrels of oil that provide these other petrochemicals that we need.
So I think that also brings up a good point, potential for it's a stable market, maybe within petrochemical use and application of that field. And then the opportunity with catalysts. Michelle, I know you're an expert in that field. Could you discuss a little bit more on that utilization or the opportunities with the nano catalyst in development?
Yeah, absolutely. Yeah, absolutely. So when I think nano, a lot of times I just think something that's really small, nanoscale. Right? But there's also another dimension to it, which is you take, for example, a zeolite, and you can actually start almost drilling nanoscale holes into it. So nanotechnology can also be the absence of material kind of at the nanoscale. And it goes back to what something Sally was mentioning, that in a barrel of oil, there's a lot of products that you can potentially make. The issue is that many times those molecules are too big to effectively interact with a nanoscale catalyst. And so what we also have to do is be able to look at this from a different perspective, which is to start making things like hierarchical zeolites, materials that have many, many different dimensions, micron-sized pores, nanoscale pores, to be able to do the types of complex chemistry that we need. So, the area of advanced catalysis in this area is frankly one of the areas where I think there's going to be some of the most amazing innovations. One thing to keep in mind though with catalysts is it's not just the catalyst, it's the feedstock, it's the products you want to make, it's the temperatures used, it's the pressures you use, it's how you regenerate the material. And so you can't, as a material scientist, just put blinders on and just look at the catalyst itself. you've got to look at how it integrates into the rest of the system. And so just building on that a little bit more, I do think if you're setting a time frame for like 4 to 5 years for some of these innovations, things that can drop in to existing infrastructures as opposed to completely revolutionizing an entire field, and now you've got to modify the upstream, the midstream, and the downstream processes. If you can figure out technologies that can be kind of a drop-in or a replacement, they're not incremental, they can be game-changing. But if you don't disrupt the entire supply chain, you're going to be able to get to this 4 or 5 years. For things that are truly, truly disruptive, I think you're looking 20 years, I would think is probably a little bit more along that timeline. So as a nanotechnologist, look at the integrated system. It's not just, I'm going to replace this with this. You're impacting an entire system.
Thanks for bringing it back around that, so I didn't have to talk about specifics of catalysis, which I haven't done since my graduate school days. Yeah, interesting thing, when you look at what the Infrastructure Act and these very significant pilot scale projects that DOE is going to be launching, they actually are really important because establishing that infrastructure and establishing this even with non-nano-enabled applications does then provide that forum for insertion, right? That's something that, if it's something that scale where then there's opportunities to improve efficiency, lower cost, however it might be, then those people should be paying attention to what those things are as they get scaled up and the technologies that are embedded in them. So that's really important. And the other thing that's important in the nano community, where meetings like this and the Nano4EARTH is so important, is elevating those topics within the people. I mean, people working on a material have as a researcher, have a lot of different directions and applications to think about. So having these kind of communities, elevating the issue, connecting those communities, and hopefully institutionalizing them in some way, so that people who are working on this think about this and are aware of some of these large things and maybe make those connections and start thinking about how can I, what's going on and where can my research plug into these things and be deployed in that big picture, I think is very, very helpful.
I think that definitely brings up a good point to think about the drop-in technologies and keep it moving. Because myself, I come from fundamental research and want to publish a paper, make some new outcomes, but it's not necessarily with the mind of where it's going to go to next. So I think that point of communication with the NNI and all the members develop here might be a good opportunity to help lay some of those pathways in a way of where it's going.
Could I just add a point to that? So, I think that the industry that is in the materials synthesis manufacturing business is, very well aware of the exciting developments that are taking place at the universities and, the publications that make it to the leading journals and, but you talk to the industry and they say, well, yeah, that's really exciting, but this is such fundamental work. It's so far from being able to be that drop-in replacement that the gulf is just too big between much of the academic style research. So we need to figure out a way to start not only inventing these cool new materials, but synthesizing them in quantities that could be practical for then incorporating them into devices, so that the industry can begin to take a look at, well, gosh, could these perform as either drop-in substitutes or small modifications to device architectures? And I think that would help expedite the commercialization cycle of a lot of the amazing work that's being taking place today.
Actually,
so I'm gonna add to that as well. So I recently moved to a startup, and I'm actually really, really excited about it because the rest of my career has been spent in large companies where when you need an innovation, you go and you try to search for a startup that could maybe be a solution to your problem. I think there's a lot of potential with the small business, large business, multinational companies, for example, having a higher level of comfort with working with each other, right? So a large company is going to know what its risks are, how to market something, how to manufacture things at scale. Startups are they're innovative, they've got all these ideas, they might not always be able to focus on the right things. But being able to get people together in a room to start saying, okay, this is the potential for my material, but then a company saying, but yeah, this is my biggest risk, or this is why I'm most nervous about it. If you can start having those conversations and getting the innovators together with the integrators, then you can really start to make what I would consider to be some pretty phenomenal progress. If you just work in a vacuum, then a startup's just gonna be innovating new materials, and a large company is always gonna be saying, well, I'm looking for something new, and they're just gonna be making incremental changes. I think there's a huge potential to get the different types of organizations that are motivated by different things together in the room. And that's one of the values, I think, to these types of meetings is you just hear different perspectives. And you recognize that a single person here isn't gonna have all the solutions. They're gonna have a piece of the solution. And the goal is in this room or online is to find the other people who have the same types of challenges or who have a material that could actually solve your problem. So it's trying to put these connections together in a meaningful way. And then also learn from each other, right? Get in a room and learn and begin to appreciate, oh, my material that I think is the most amazing in the world is actually gonna cause all of these problems. Now I can begin to understand how to continue to innovate it. So look at it from a risk perspective as well.
I was going to make a comment on scale up in the nanomaterials, but actually we have a question from who I was going to reference when it comes to scaling up.
Appreciate that. So I just want to get your thoughts on, because when you take these nano innovations or anything in the industry and try to scale it up, the lack of being able to predict things at different scales leads to a lot of time and cost. Right? And I think we're talking about near-term stuff. You got to go to private financing or government, but cost and time is a big issue, and a lot of that's eaten up by endless testing of things. So I just wanted to get your comment on what role you feel like nano can play in adding predictability, right? Because if you think about a lot of the systems for the grid and for power electronics and inverters, a lot of the things that are assembled, there's no good way to predict their failure modes. And we're out here looking at things that would naturally be in temperature shocks and things like that. And it's just interesting to me, to me, if you look at the space industry, a lot of what has enabled new space is digital transformation and being able to predict things better. So I just want to throw that out there, maybe for you all to comment on your thoughts and how you feel that nanotechnology from a material standpoint could feed into better predicting systems.
Maybe I'll take a crack at that one. Yeah, I think that's really a great point. So what would we like, right? We would like a way to create digital twins for chemical conversion devices that are based on sort of multi-physics, multi-scale processes. That would be the dream, right? And that it was easy to do. It was easy to build a new digital twin. Right now, like every digital twin might be 2 or 3 PhDs strung together that sort of do all the science, right? So wouldn't it be awesome if we could basically have a toolkit where you could go and say, okay, here's my new material, here's the device architecture, here's all the right physics and chemistry, and it could allow you to do that. Actually, fusion is an interesting area where they now have really pushed on the computational aspects of being able to increase predictability, and that's been part of the transformation that's been occurring. So I think this is another area that's absolutely ripe. It's ripe in terms of computational capabilities now. AI, a lot of people are interested in using AI to build reduced order models for some of these processes. So I think it's a really great time to try to do that, and that would be a great role for a community like this to play, is to really bring together all that right people to make that happen.
So I have a slightly different thought about this, and I'm not sure if this is what you were going into, but if you're thinking about digital twins or, I guess, infrastructure resilience in some way, the key piece of information, in addition to modeling, is data, and that. So actually, historically, people have spent a lot of time, talking about nanosensors. But this could be an area where if one needs to understand the state of various parts, whether it's a surface or a mechanical component or something where, you go back and think about the early days where people were talking about ubiquitous sensing and nanosensing and low power sensing, where those sensors are providing a data stream about the state of the system that you're looking at, which could be obviously fed into a digital twin to predict based on those sensors what's about to happen in terms of mechanical or system resilience. So it's a sort of interesting angle on essentially an old conversation in the nanotechnology.
And I'll take it in a little bit different direction too, because one of the comments that kind of struck me about that was when you were talking about scale up. And I think back to when I had a team that was working on innovating new types of membrane materials. And immediately what you typically would go to is you'd have some type of cost objective. You'd say, okay, we need this material at, I don't know what is $1,000 a kilogram, or you'd have some kind of financial target. I think one of the interesting things about nanotechnology is you often don't need a lot of the nanotechnology to get the benefits of having a nano-enabled solution. And so going back to my membrane example, we want to do a very complex separation. And the molecules that were, or the nanoscale materials that were able to do it were incredibly expensive, like millions of dollars a ton or something. But when you did the math and you looked at how little nanomaterial you actually needed to be able to achieve that great separation performance, you realize that like a gram could cover the membrane the size of a football field or 10 football fields. Cost no longer becomes really the issue, because the nano-enabled solution provides just such a phenomenal benefit. And then in that case, you'd have a nano-enabled solution, but the scale up of it is, you're not looking at kilograms or even 500 grams, right? You're looking at just really, really small quantities. So I think in some application areas, and certainly in catalysis, I would say, no, you need millions of tons of that material. But in other types of nano-enabled solutions and nanotechnologies, sometimes you just need a little bit of it. And so scale up isn't so much of the challenge. So I think the economic evaluation for these is sometimes a really, really informative thing to look at.
Thank you. Before we change topics, we have a question from online.
Oh, no, yeah.
Oh, sorry, I thought you were
It's all good, it's all good. So you mentioned some challenges with nanotech and scale up, including, predictability, health, and, public perception. Are there some other kind of unique factors with nanotech that need to be addressed for scale up?
I've got one. It's around things like critical minerals, availability of certain, iridium, for example, platinum. We hear about lithium, we hear about cobalt in a lot of lithium batteries, for example. The supply chain, being able to get these, and then also, in some cases, the environmental impacts or risks to being able to mine those types of materials, I think is something that's very important to be able to consider. I think that's why in some applications you need to be looking at things like recyclability, the ability to recover and reuse materials. That becomes a part of the engineered solution, if you will. So you might take a hit on performance or long-term performance if you can recycle the material a bit more efficiently. So I think that's definitely an area that is a big concern for a lot of these technologies.
Just have to put my NIST hat back on and say metrology. All right, so again, that's always a historical challenge, especially as you're trying to do things in process control or real time. Having the right measurement tools at the nanoscale is historically a challenge to look at those kinds of things at in real time and in large volumes or large high speed and all those kinds of things.
Maybe I'll just add one more thing about the critical materials. There's a strong focus on maximal performance of a component of a device that could drive you towards picking these, rare and costly materials. to the extent that we can really begin to look at substitutes for these critical materials, and maybe the performance is 20% less efficient or whatever. On the other hand, when you look at it from a systemic point of view, a systems point of view, including supply chain and security and all of these other issues, maybe we need to start thinking about how to go to these second and third best, because they don't suffer from some of the risks that you talked about.
Right.
Thank you. And from the online community, we have a question for Dr. Ostrat. A lot of industrial separations have been driven by the use of petroleum feedstocks and the use of these feedstocks for both transportation and chemicals. But as the use of petroleum feedstocks declines, won't the need for separations diminish as well? And this was from Sam Brewer at NanoBiz.
Hi, Sam. It's good. It's good to know that you're online. I think there's going to be a need for separation technologies. I mean, even things like the incorporation of materials into foods, for example, requires a certain level of purification. I do think that a lot of the membrane separations, for example, that have been developed by the petrochemical complex, if you will, also have applications and utilization, for example, things like CO2 separation from air, for example. And so I think there's a lot that can be repurposed, if you will, from the innovations that have already been developed.
Maybe just adding a little bit to that. So if you look at the electrochemical processes for reducing CO2, many of them create multiple products. You don't get all of the product that you want. So separations are still going to be really important until we get to the point where the selectivity for making what we want to make is so high that we don't need to worry about that. So I still think it's critical.
And I think the mention of electrochemicals is a good segue. I think we got time to maybe start delving into one more topic. And we all brought up batteries, power grid, and that was actually a very common theme in some of the pre-work that we saw in feedback from the people in the audience and online. So I'd just like to open it up for nanomaterials, fundamental challenges when we get into power and energy. Maybe batteries would be a good starting point over the next 4 to 5 years.
I'll start with one comment, which is, to me, saying batteries, it's so broad, right? Is it for transportation? Is it mobile sources? Is it a handheld device? Is it to power a car? Is it for grid storage? And to just say battery, I think lumps too much in one term. And so I think we need to start getting more specific about, kind of an application area or coming up with something, because talking about battery to me would be like saying it's too diffuse. And you've got so many different challenges and parameters and priorities such that they don't all fit together in one.
So there's a lot of room to tailor it towards specific applications for the materials that are being developed.
Yeah.
So since DOE has spending billions of dollars probably over the last 10 or 20 years on this.
Absolutely, yeah. What you want for a large grid-scale storage battery, it can be heavy. You want it to be super cheap. You want it to be efficient. That's completely different than what you want for putting in a car or putting in a ship or putting in an airplane. So yeah, I think you're absolutely right. It's a huge field, and different solutions will work best for different applications. And the economics of the different applications is also incredibly different, right? The battery you can put in a car, you can afford to actually spend quite a bit of money for that battery, whereas the battery or the storage system that you're putting onto the grid, you need that to sort of compete with things that are a penny or two a kilowatt hour. Entirely different.
So obviously, I focus on things maybe people aren't thinking about with the EV market certainly is driving huge amounts of work in that battery space and production. So I don't think there's any shortage of attention on nanomaterials for that kind of energy storage. But talking about larger, it's really again about that energy storage challenge. And so I talked about all the different ways, and we're thinking about that just in terms of from a scientist and thinking where might I contribute, it's really there's really tremendous number of opportunities everywhere. So even in an area that's a little bit odd, which is gravity-based storage, for example, where people, in some ways, very low tech, right? You just take a big weight, you raise it up, you have energy, and then you lower it down. But if one thinks of all the opportunities from lightweight, high-strength materials to lubricants to potentially magnets in any kind of energy capture system, there's probably opportunities for nano-enabled technologies throughout that entire system that could make that relatively, what seems like a low-tech energy storage solution, more efficient or more reliable. So it isn't, there's opportunities to think outside the sort of the battery box, I think.
Mm-hmm. Yeah, your mind could go to nanoscaled electrodes, cathodes, membranes, but then you also have corrosion-resistant materials for different types of systems, fail-safe, right, fire suppression. So there's, I just think a lot of opportunities for advanced materials in the entire battery space.
Yeah, I mean, that brings up a fantastic point. As we break these down, all the opportunities with nanoscale materials to help enhance those opportunities are very broad. To zero in on just one that's going to make the difference, that's very challenging at that point. I think we've got about 5 minutes left before we shoot it over to Q&A, but I did want to touch with you, Michelle, on occupational safety and health.
Okay.
With some of the materials that we're talking about here, I think some of them might be more bulk materials at nanoscale. Would you be able to just make a comment on any considerations as this technology is developing that we should just keep in mind if it is going to be scaled up in a commercial format?
Yeah. So when I was involved in the Nanoparticle Occupational Safety and Health Consortium, to me, that was actually a really inspirational time in my career, because what I realized is that at least the companies I've had the honor and privilege of working with and the colleagues and peers that I've worked on, occupational safety and health is taken very seriously. I don't know too many, I don't know personally too many organizations that would discount that. And so I would say, first of all, the ES&H people in companies and organizations, they're really genuinely great people, from my perspective. And I think that was just an example of where a group of concerned scientists, ES&H people, chemical hygiene officers, said, we're going to do the right thing from the beginning. And to me, it was just a really encouraging thing. It has spawned a lot of work, for example, now in things like uses for nanoscale pharmaceuticals, because as part of that, people understood what some of the occupational safety and health concerns could be. It spurred a lot of work in, for example, environmental remediation using nanotechnology. So there's always some really interesting, good offshoots also from that work. The other area I would like to mention, because I think it was also something that's somewhat neglected, but I do think is really important and is something for the United States also to maybe prioritize a little bit higher, is trying to figure out how we can get more engaged with the standards organizations, ISO, for example, because that's an area that's got some economic competitiveness. I know other countries can often position themselves in their industries to be very protective if they get standards written in certain ways, and I think that's just an area where we need to apply a little bit more attention to that, instead of it being in some cases kind of being an afterthought. When I spent time at ISO, it just struck me how many people, it was actually a volunteer thing for them. And it was, I think there are just some opportunities there for the United States to come up with some type of a strategy and an investment in being able to make sure that our standards are well thought out, they're well informed, and they've got really good technical participation. So I'll just put a plug in there for that.
Fantastic.
So just on that last point, the CHIPS and Science Act actually included a little known provision that provides funding for NIST to help essentially help convene and engage larger numbers of industrial people in the standards organizations. And in fact, this is a somewhat related thing. the nano EHS issues are very, well developed, and there's actually very strong communities, and I think they are up to this task. And then when you get into thinking about newer materials or things that aren't already, through the regulatory process, or like I was talking about earlier, then that's an opportunity to engage multinational fora like the OECD, Biotech, Nanotech, Emerging Technologies Group, places where you can have these global conversations, so we don't get at crosswise with other parts of the world. So I'll just sort of put a plug in for those kinds of approaches.
And actually, kind of along those same lines, as the federal agencies are starting to develop their climate strategy and implementation plans, a lot of these technologies are tied in there. When we think about the NNI, what are your thoughts on some of the ways where the NNI and the federal agencies can help lower that barrier of entry or provide more opportunities for the researchers in this community? Actually, Lloyd, could we start with you?
So it's these building communities of interest, communities of practice, and convenings like this. It's really about bringing the different sectors and different interest groups together, early in ways to make those connections and build those communities. I would say would be the best approach, other than funding, which we don't control.
Yeah. I would say helping also to run some traps. And what I mean by that is, for example, go back to the carbon sequestration. There's just a lot of challenges in terms of permitting, and that's just an example. And a lot of these companies who are involved in sequestration, for example, might not know all of the permitting requirements that happen. So just being able to help provide some expert guidance or being able to foresee what some of the unanticipated challenges are, I think would be a good way to help streamline some of the innovations actually being deployed into market.
Okay, I have a little bit of a list. Sorry. So the first one, I'm going to speak through the lens of a academic research community who is heavily engaged in innovation in this area and has been for 20 years. The typical experience is that you get funded by the government, you do a project, you have some really good result that's really exciting, and now the next thing is, depending upon the level of the maturity of the technology, you need to then find another funding source or maybe get industry to support this, but then there's a hiatus, so it takes a long time. Maybe the funding you can get isn't really like the optimal direction. It's sort of adjacent to where you wanted to head, but hey, you want to continue. So finding a more seamless way to provide steady support throughout the innovation cycle. And I know a lot of federal agencies now are trying to improve this, but I think that there's a careful monitoring of what's working and what's not, and developing new mechanisms to really try to keep the path straighter and narrower towards that ultimate commercialization would be very helpful. So basically avoiding disruption in the innovation cycle. And an important part of that is the provision of translational research facilities. So we heard about the Department of Energy's 5 nanoscience facilities. NSF also supports some of these facilities, but broad access to translational research facilities where you can take that super cool discovery, you can figure out how to make quantities of it that are meaningful to be able to incorporate in a device, to then access to machines that allow you to build, that next generation battery that provides all the, excellent testing capabilities you need, including, probing with the best, X-ray microscopy or whatever it is you need. So really trying to make translational research facilities available to the broad community would be very helpful. Finding a still better way for public-private partnerships and pre-competitive partnerships where you really sort out the IP issues in advance, so that does, because that's often a big barrier too. I talked about disruption in the innovation cycle. It often takes a really long time to establish those agreements. So could there be, new thinking in a world where we need to compress the innovation cycle from 20 to 30 years to 5 to 10 years? It's and the next one is, so we've heard a lot about this, about creating the community. So I think getting a cohesive innovation community where learning is quickly transferred between all of the different community members. And that means not just innovations, but challenges. We heard about the need that people need to understand where are the sticking points so that people can work on the right problems. Another key dimension of this is finding sort of stepping stone markets that enable you to take technologies that are way too expensive, find those early markets so we can begin that learning by doing cycle. Solar is the perfect example. It was the space program that decided that photovoltaics could be a great way of getting electricity in space. But for that, it would have been much longer. So in all of these areas, are there stepping stone markets through DoD or other high-value niche markets, and trying to identify those and matchmake between them? What I like is green products, like you can actually get dark glasses that are completely made from CO2 recycled from the atmosphere. Super cool. People pay a premium for them, but zero emission things. So there are people willing to pay for those. So trying to get that community, and again, sort of going back to this supply chain issue. This is really encouraging from an early stage to think about those materials that are not going to be limited and rare. Will slow down development. So I think that whole portfolio of things together, there's a big opportunity to really further propel this community that's already doing such amazing things.
So that's fantastic. That gives a full line to work with from start to finish for it to go. And actually, the translational facilities, I actually looked in the talk this morning with the DOE. I didn't know those facilities could be free for users and everything. So with the ones you mentioned, does that tie in like a faux America Makes, any of those type ones, or are they different?
Well, notionally, I think it's certainly aligned with that. If America wants to make, we need to start, making it a lot easier to make things. So finding and articulating those that need and building it into a larger industrial policy that makes our innovators more competitive at designing new products that are commercialized and made in America.
So I want to build on, I think it was the second item on your list. So a couple of years ago, I went through a NSF program. It's called I-Core. If you're not familiar with it, you might want to take a look at it, but it was a really fascinating experience, because you have these startups who think they've invented the next greatest, medical device or something. And as part of the NSF I-Core program, they actually go out to prospective customers and actually figure out, is this your pain point? Would this solve your problem? No, it wouldn't solve your problem, then what problem does it solve? And then through a journey of trying to understand your customer, it created a really nice alignment between what the innovation actually is and who would be willing to start to commercialize it. So just if you're interested in learning more about that, the NSF I-Core is a great program, not just for the the innovators and the entrepreneurs, but I participated as an industry mentor. And so it was a really good way also to give back and to give a perspective and try to coach people who are just really excited and enthusiastic about their program. So just a pitch on that.
And just adding to that, so DoD through, I think, ONR has similar programs. I think 5 or 6 universities, and yeah, they're amazing. To go out and interview 100 people and say, what is it that would solve your problem?
Yeah. I think X-Tech is one with Army. That does offer that mentoring.
I think I'm looking at Andy, but I think DOE is also participating in the I-Core, has a very high program, and NIH.
Okay.
Question from the audience?
Good morning. Hello. Good morning. Company name Applied Plasma Technologies, Marshall, Virginia. I would like to follow the explanation about how to convert promising nanotechnologies into high scale. We have, and back to panel title, identify one of, I would like to suggest one of technologies. It's boron nitride nanotubes production. That's US invention. It was invented in 1995. 10 years ago, we built the first industrial scale equipment. And this technology allows, for example, if you add 1% of boron nitride nanotubes to aluminum alloy, it becomes as strong as steel. Can you imagine how much greenhouse gases we can save on aluminum production, steel production, and on and on? It's one of the ways how to save CO2, just improve technology. And at the moment, this equipment doesn't have market. Potentially, we have market, but we need scalability because the capacity is about 20 grams per hour. If, for example, Tesla will produce 500,000 cars per year, and everybody needs about 80 kilograms of aluminum, we will produce this amount centuries. It means we need improve this technology, production technology, and we don't know who can help us. That's, I believe, an NI initiative maybe will help us.
Yeah, I think that's a really good example of something that's really interesting, that it would be nice if we had a better way to pursue that. I think there are probably many examples like that where we just have not been in the business. It's not been the primary focus of the R&D infrastructure to be able to support those kind of things. I think that that's a big opportunity that we should figure out how to do that. Oh, absolutely, yeah, I didn't, yeah.
Joint tests, joint programs, develop joint proposals.
I think that'll be a good opportunity in this meeting. We can find room to discuss more.
Philip Lepel from the MIT Washington office. So many interesting things that tempted to comment on, but I want to follow up on what Michelle brought up about I-Core and things like that from the following perspective. We've talked a lot about facilities and a little bit about programs, not so much about people. So Sally, in your example, in the sort of canonical picture, I think now it's not, the professor who started the research who goes and does the company and takes it on the next stage. It's the graduate student who goes to I-Core and decides they want to be the CEO of the spin-out company, which then gets acquired by the big company that Michelle talked about. And the faculty member maybe is a board member and scientific advisor. But so this, I guess, in both if you really want to talk about what can be done in 4 or 5 year timescales, right? Then in both the human resource side, the people, and in the programs and connections of the programs, I think we need to kind of get away a little bit from all the pipelines we have and talk more about pathways models. So I just wonder what you have to think about that. I mean, for example, in the program side, right? We heard about Office of Science, we didn't hear about RPE, which is, in some sense in a position to short circuit things. And we usually think of it as being at the close to commercialization end, but in fusion, for example, they've identified, pinch points earlier on and put resources there. And so more of those sorts of things and of things to help students or people at other stages in their career learn about whether it's the commercialization, whether it's the soft regulation stuff like standards that you talked about, but all these other things that have to be part of the innovation ecosystem to make things happen quickly.
Yeah, I think that's a great comment, and again, going back to, you know, one of the opportunities that we have here is again to build that community. And I agree with you. The technology is one piece of it. You know, being in large companies, I've seen small companies be able to get into that large company if you've got a champion, right? Or you've got somebody who really believes in you. And it's interesting how many times when the startup approaches and they promise X, Y, and Z, after working with the large company, they say, you know what, X, Y, and Z just isn't where it is, but it's over here. And they can still make both parties very successful. It's just that the original pitch, I guess, if you will, from the startup had to be massaged quite a bit, where something else, you know, pops out the other end. And I think it's really having people be able to understand that they don't have all the answers, right? And that if you can get in a room and start talking and actually figuring out what is the opportunity, what is the need, and where are the challenges, you can come up with a better solution. I've seen in both sides people who are just ardently rigid in this is my technology and this is the market, and people saying, but the market's over here. If you don't listen to them, I don't know how successful that's going to be. So if you can learn and adapt and be willing to take some risks and listen to each other, I think that's where a lot of the innovations really can happen. But I like the idea that it's not just, you know, the user facilities are really important, right? But you can also see, for example, a lot of incubators starting to come up where people are teaching people business models, they're teaching people how to put together financial plans. Those are also really important parts of this entire innovation process that we have to do. And I think you're starting to see those with some of the, like the career coaching and the incubators that are starting to come along and adding more of that personal and relationship balance to it.
I had a thought, and I'll say this is a poorly formed thought because your remarks just brought it up to me. I think it would be really helpful if we had some kind of way of making an assessment of the health of the innovation ecosystem. You know, wanting to understand, you know, how many of the good ideas are actually finding a pathway and able to navigate, you know, what is a string of near-death experiences, at least as far as I can figure out, and do analytical work that informs us what's not working, what's broken, and what are we, you know, and how much are we leaving on the table that we could be integrating, and that would help inform our strategy about what we need to invest in, but also just sort of the ecosystem support that we need to provide to keep this working well. So, you know, much like a company would you know, do this kind of assessment of their own activities, having a community level assessment would be very valuable, and I think that's something this community and this organization could think about how to do that.
Yeah, this is great, because actually we're touching on the T in our EARTH acronym here for training. It's actually going in a direction that I don't think I originally envisioned there, but fantastic area for training and improving in the community. So I think we got time for one more question. Or?
All right. Thank you, and Sally kind of touched on my question too. I was going to pick on you a bit because I'm a heat transfer guy, and one of the first things you mentioned was searching nanofluids. So I started working on nanofluids in 1999, and I've been working in nanotechnology for a long time. And moved into carbon nanotubes, went to grad school, became a professor at Georgia Tech, taught nano courses. One of the things that we could do as a community, which relates to what you're saying, is that being here in this audience, I've heard nanofluids, graphene. We talk about the material set, but the form factors matter a lot. And I think in terms of finding successes at the intersection of material and form factor, because the problem for the application of the system is determined by form factor, is important for us to do, right? I operate a company that spun out of Georgia Tech that makes more line carbon nanotubes than have ever been made, and we have commercial products, but nobody has heard of us, right? I go and talk to people and say, oh, why haven't we heard of that? A lot of it's because I spent about 8 years never talking about it. And the reason is because so many negative opinions have been developed about things without having specificity that we don't say this in our community enough, but we kind of have to honestly say that we got to kind of clean up the negative opinions a bit. Because when you go in to talk to a customer or someone in the industry about graphene or carbon nanotubes, the first thing that runs through their mind is like something that's ridiculous, right? And then you have to go and either it's that or it's something that sounds really good, but it's not practical. And so just being able to, in looking at our community and finding the success cases of material and form factor, and being able to educate ourselves, right? A lot of us have been in this for a long time, but it's worth a fresh look. And I think if we had an ability, we investors, potential integration folks, to look at that data set, it would save a lot of money and time on things. So, just information for comment too.
Yeah, I think having, you know, a library of case studies that are accessible to, you know, a broad group of recipients of that information would be super helpful. I know it would be helpful for me. I mean, I'd love to be able to point to, you know, here's this story, and this was the idea, and this is how it made its way through the pathway, and here's the cool new impacts that it's having. That would be great. And again, I think another thing this organization can do is have those success stories in enough detail and fidelity so that they, you know, that they've got enough information to influence the way people think about this field.
I think I spent my entire time at OSDP looking for those examples.
Maybe with this community, we can keep that story in there. So actually, I think, you know, we're running up on our time, but I think we covered a lot in our hour and a half here, going from technologies, health and safety training. You know, I like the, you know, when we're talking about short-term goals, in 4 to 5 years, like was just mentioned, not to overhype, you know, overpromise, you know, that can happen in some of these fields, but have realistic approaches and how we can get there and get the right communication started and ensure that us at Nano4EARTH, as we, you know, push this challenge forward, that we're looking into the right things that the community wants to address and that we're providing the right help. So with that, I'd like to thank our panel one more time.
Yeah, and I think you've given us a lot more to continue to think about. I think we're taking a short half-an-hour break for lunch. For those of you who came up through the metro, that's basically, there's a food court down there that gives you a lot of good, diverse options. But we look forward to welcoming you back for panel 2, which I think we're starting around 12:35. Yeah, all right. Thanks so much.